So I'll get rid of the read now. In theory, shouldn't need to after we go through this. All right. So what we did last time, we talked about how I say a lot. I guess I don't know. No, right on cue. We talked about how when we're dealing with tangent planes at extrema, that in order to get those tangent planes, it turns out that our first order partials tend to either be equal to 0 or they don't exist at all. Right? If anybody's looking for a typo bonus here, look at the difference in size there. That just looks hideous. Right? So whether it's a typo or an Easter egg, either way, it's a bonus point. So conditions for local extrema, it's just like in Calc 1, you're not going to have a local extreme value unless it occurs at a critical point. And the critical points only occur when the first order partials are equal to 0 or if they don't exist at all. Sometimes you can determine the extrema just based off of the nature of the function. I mean, you could almost always, if it's one of the classical surfaces, what we call quadric surfaces, ellipsoids and paraboloids, basically anything that you recognize as an ordinary function from Calc 1 or even pre-calc, like a parabola just extruded out into free space. Those are ones that it's usually pretty easy to identify the extreme values for. Like, for example, in this problem here, here's the graph. I know that there's an extreme at this location. Right? I'm looking at a local max. I'd want to be able to figure out the value of that local max. There's a bunch of different ways you can do it, but the one of the ways that's, I don't want to say it's a surefire approach, but it's as close to a surefire approach as we can get. It's called the second derivatives test. And we'll get into why this works the way it does down the line, but for now, it's just a process. So the second derivatives test involves us determining the first and second order partials and using that in a formula called the discriminant. That's Pythagorean in nature. And that's the explanation that's coming down the line. It's just to go through the process and also the proof behind it in one class is just too much. Right? So we'll do process this time, we'll do proof next time. But that discriminant helps us determine, if we categorize it the right way, whether or not we're dealing with a local max or a relative max, a local min or a relative min, a saddle point, which is, it's, the definition's right there. But if you understand that definition at first glance without any additional research, I mean, that's a classic textbook definition. It doesn't really help. What a saddle point is a point that satisfies a lot of the conditions for local extrema, but maybe too many of the conditions. Right? So a saddle point satisfies conditions for being both a local minimum and also a local maximum really at the same time. Because remember, in 3 dimensions, you're not just coming in from the left and from the right. Okay? So if you imagine that you're climbing up a hill from one side, so I'll just try to get ready for this diagram. So you're climbing up a hill from one side. And this is an attempt at drawing a surface that involves climbing up a hill from one side. All right. And then from another direction, so from this direction, you're working your way towards the max. All right. So let me just make that clear. All right. And in fact, you might even look at it and say, we got a relative maximum at this location. You're working your way up the mountain. So let's say you're just following a particular path along a path along the path, but then the path takes a sharp turn, and maybe it doesn't go vertically, but it does start, it turns in a different direction, kind of like a ski slope. What's happening is you're getting to a maximum from this direction and you think you're going to a maximum. So let's say it's right here. You think that's a local maximum, but only because your vantage point is bringing you in from this direction, right? You can't see what's going on over here. You can't see any of that. You can't see what's around the bend. So from your vantage point, it looks like you're approaching a max. So if you never even consider what's around that corner, you'll think that you got to the highest point and that's the end of it. And the best you can do is go back down, right? But the person that's skiing down the hill from this direction, they're approaching something else. Same location, but they're approaching it in a different context. They're approaching a minimum. Right? So you got a snowshoer that's walking up a hill, doesn't see what's going on beyond the turn. They think they're getting to a maximum point. And then you have the skier that's coming down the mountain that doesn't see what's beyond the turn there. They think they've gotten to the bottom of the mountain. So they're getting to a minimum in that trip, but it's only kind of a temporary minimum. Their minimum is somebody else's maximum. All right. That's an example of a saddle point. Right. The classic example of a saddle point is actually a graph that looks like a saddle. I'll show you that later. Right. But you could see, hopefully, I mean, my diagram is pretty bad, but hopefully the explanation kind of helped a little bit. It's the idea that from one direction, it appears to be a maximum, but from another, it appears to be a minimum. It's kind of like the idea of a limit. It's got to have the same meaning coming in from every possible direction. So it's got to be a maximum point no matter which way you go. So if you're thinking of like the top of Mount Everest, like the tippy top, that's a maximum, because no matter what direction you're climbing that mountain, no matter what direction you come in on, you're always approaching the same point, which is the highest point. All right. So you see the question here, it's intentionally vague in the sense that I don't want to force you into one approach or another, because there are actually a couple of different approaches that you can use. One is the second derivatives test, which we're going to get to in a sec. The other is just algebra, right? And I can actually show you that one real quick. The algebraic approach is actually kind of nice because, and I'll just write it here, algebraic approach. You're looking at really a conic section. If you look at the variables that are in play here, you have a negative x squared plus 2x, I'm reorganizing it a little bit. Then you have a negative y squared plus 6y, and then you got that negative 11, and the whole thing is equal to f of x comma y, which I'm just going to write it down. All right. So what you can do, I mean, if this seems like it's going into familiar territory, it should. What we're going to do here is complete the square, come up with the value that makes the perfect square trinomial. And I love the symmetry of when, as a teacher, when I'm teaching this for the first time in one class, and I can now tell them that, hey, in my algebra 1 class, I'm teaching completing the square for the first time. I'm like, you're going to need this because I can tell you in Calc 3 they're going to be doing it too. And here we are. Right? There's a bunch of different ways of doing completing the square. I like the b squared over 4a approach. Some people like the process where it's like you take the b value, you cut it in half, and you square it. But then I find that those folks tend to forget to divide by the leading coefficient. So for each trinomial, we compute b squared over 4a. That's my preferred way of doing it. And if you're comfortable completing the square to the point where you don't have to worry about what I have to say about it, then by all means do it any way you want, as long as you get it right. So for each trinomial, we compute b squared over 4a. The b value is a 2 squared over 4 times a -1. So we're looking at 4 divided by a -4 is -1. So that's what gets chucked in here. I just mysteriously subtracted a 1 from an expression. I can't just do that. So I correct for that by adding a 1 onto the other side. Well, not to the other side, but I add a 1 onto the expression itself. All right. So 6 squared over 4 times another -1. 36 divided by -4 is -9. So I subtracted a 9, so I correct for that by adding a 9. And it keeps the equation balanced. All right. So I'm looking at f of x, well, f of xy, and I got this trinomial here. I lost my color scheme here. I want to change this to a yellow. I got this trinomial, which now has a leading coefficient of -1 that can be factored out. So we're looking at x squared minus 2x plus 1. And then same idea for the other one. The trinomial, pull out a negative, we're talking y squared minus 6y plus 9. And then we can combine the like terms. It's really -11 plus 10 is going to be -1. All right. So then you look at this and you say, okay, well, we're going nowhere in a hurry. Well, negative x minus 1 squared minus y minus 3 squared minus 1 would be the equivalent. So we're not completing the square to solve the equation in any way. We're completing the square to get it into a standard form, right? At least as close as we can get. So this is what we're looking at here. Now, if I reorganize it as -1 minus x minus 1 squared minus y minus 3 squared, then believe it or not, just by looking at this, I'm able to come up with the maximum, the local max. Because what's happening here is I'm starting off with a fixed value of -1. So this is our fixed starting point. And then I'm subtracting a positive value. So this expression here is positive. And this value is positive. So if I subtract two positives, regardless of what I put in for x and y, I'm always going to be reducing the value of -1. All right. So there's no way I can actually get a number that's larger than -1. So no way to get a value larger than -1. Therefore, -1 is the local max. As it turns out, based on the nature of the function, because there really is no way to get a value bigger than -1, in this case, it's actually an absolute maximum. So it's local in the sense that it's the high, it's the king of the hill. You heard, I'm sure you heard an analogy like that back in Calc 1 and Calc 2, where it's the highest point compared to the points immediately surrounding it. Right? It takes on a different meaning in three-dimensional calculus because now it's in every direction rather than to the left and to the right. Right? But not only is this the point that's the highest compared to the ones immediately surrounding it, it's the highest out of all possible points in the function. Right? So it turns out it's the absolute maximum as well. So that's one way to do it. Fun.
Professor?
Yeah.
Just a question. If we didn't have that fixed -1 there, like if we had just negative x minus 1 squared minus y minus 3 squared, can we consider the 0 as the maximum
Exactly.
number?
Exactly.
Okay, okay, good, good. Thank you.
No problem. So the alternative to this, because I mean, when we're looking at something that's polynomial in nature, not everything's polynomial. So there's that. And there's also the fact that even if it is polynomial, maybe it's not something that's easily put in an appropriate form, like an appropriate standard form. Honestly, I can't think of an example off the top of my head where it's polynomial and it wouldn't work out in a reasonably clean way, but I'm sure I'm just not thinking. All right. So what we would do is use the second derivatives test, which involves just differentiating the living daylights out of the whole thing. All right. So what I'm going to do first is find the first order partial with respect to x. I could actually pick up my marker now. Oh, I just closed the file just out of nowhere. I'll be regretting that later. So out of all of this stuff here, if I want to find the first order partial, I said first partial. I just made up a word there, combo word. First order partial with respect to x, I could ignore anything that's solely in terms of y. I can ignore anything that's constant in general. So I'd be looking at negative 2x plus 2. Right. Everything else zaps away. Then first order partial with respect to y, negative 2y plus 6. All right. Now we are going to have to figure out our second order partials, f sub x, x, f sub y, y, and the mixed second order partial. So we might as well just bang that out. I mean, it's going to happen anyway. So we might as well just take care of that too. All right. So f sub x, x would be negative 2. F sub y, y would be equal to negative 2 also. Where'd my vertical line go? What on earth? And then my mixed second order partials, the continuous function, the original function, we spent a lot of time talking about how you can prove that a function is continuous using limits and all that stuff. But really, I mean, if you recognize something that's polynomial based, whether it's multivariable or otherwise, you know that it's going to be continuous and differentiable for all values of x and y, just because there's no instance in which it would be undefined or indeterminate or imaginary. All right. So that means that f sub x y and f sub y x would be the same thing. Does it matter in this case? No, because it's easy one way or the other. If I take the derivative of this expression with respect to y, I get a 0. If I take the derivative of this expression with respect to x, I also get a 0. Right? But there will come a point in time, I can guarantee you this, there will come a point in time where you'll look at it and say, whoa, f sub x, y looks like a beast. But f sub y, x doesn't look so bad. If I know they're going to ultimately be the same thing, let me just do the one that's going to be easier. Let me just make sure that it's continuous differentiable for all values of x and y. Okay? So there you go. So we have all the pieces that we need. Now what we do is we evaluate our, well, in this case, I'm kind of cheating because all the second order partials are constant. So it's not really dependent on a critical value, but I'll take you through the process anyway. So you'd have to make sure that you have the right critical values. And we get that by setting our first order partial with respect to x equal to 0. So that would be the same as saying 0 equals negative 2x plus 2. Solve for x. So x would be equal to 1. Take our first order partial y, set it equal, first order partial with respect to y, set it equal to 0. So that would be 0 equal to negative 2y plus 6, which would give us y equal to 3. All right. So our critical value, which we just abbreviate as crit, which I'm sure you've seen before. Okay. Our critical value would be 1, 3. But you could also write it as 1, 3, comma, f of 1, 3. Now indicating the z value that goes along with it. All right. So either way is acceptable, because in the case of the 1, 3, we know that you're giving an x and a y. And if you give me an ordered pair with two variables, the assumption is that the two variables that are referenced are x and y, unless there's reason to think otherwise. So in this case, any of these contexts, I'm not thinking r and theta. Let's just put it that way. All right. So we have our critical values. Now I need my discriminant at that particular location. AB is referencing the critical value, so AB. But when I go to find D of AB, you look at the formula here, it's f sub xx times f sub yy minus the mixed second order partial squared. All right, so my D is, it doesn't relate to the critical value. So I could say D of 1, 3 if I want, but it could have been D of shoes and socks. It doesn't make a difference because these are constant, right? So negative 2 times negative 2 minus 0 squared. All right. Now, the reason why we go with the f sub xy ab squared, that's one thing that I'm kind of stealing my own thunder for next class. That's really the product of f sub xy times f sub yx. Right? But since we know in a continuous function, and in order to have a local max or a local min, it has to be upon a continuous domain. We can assume that f sub xy and f sub yx would be the same. We're allowed to write this as the quantity squared, right? So I figured somebody's got to be wondering that, so why not just throw that in there? All right, so a little taste of what's to come. All right, hear a beeping sound. It's either a ticking time bomb or the water dispenser is empty. No, I don't think I'm important enough for it to be a ticking time bomb. All right. So anyway, we have our discriminant. Now we look at our conditions pertaining to the discriminant, and that'll help us draw our conclusion. Now, in second derivatives test is only going to apply to the critical value. So regardless of whether you actually had to plug a critical value into your second order partials, that's really irrelevant, right? Whatever conclusion we draw here is going to be related specifically to the critical value of 1, 3, right? So you see the first condition is that the discriminant is positive, and the second order partials with respect to x is also positive. Then we're looking at a local minimum, all right? So my second order partial with respect to x, and this piece here, I'm looking at a negative. So in this context, I'm looking at this guy that shows a relative max, because that's the case where the discriminant is positive, which is what we got right here. And our second order partial with respect to x is negative, also what we got. So therefore we have a local maximum. So therefore, local max at 1, 3. But if I want to know what the actual maximum value is, that's where the f of 1, 3 comes into play. I would replace the x, each of the x's with a 1, and each of the y's with a 3 and simplify. All right. So therefore, the local maximum is that f of xy equals 1, or you could say z equals 1. I mean, it's understood that when you say f of x comma y, that you're also saying z. It's like f of x and y are the same thing. So nobody's going to get upset if you say you just kind of drop a z in the middle of a problem when it wasn't there before. That's not going to be an issue. So you could say that where the local max when f of x, y is equal to -1, that's fine too. You could say z is equal to -1 either way. All right. Now, I got that from the algebraic work that we did on the side. I didn't get it from checking my work. It's probably a good idea to actually check my work. So that's what I'm going to do. Except in Desmos, I'm going into Desmos mode here rather than GeoGebra. And instead of putting x's and y's in, because I don't want to confuse Desmos, I'm going to put it in as a's and b's. So negative a squared minus b squared. This way it'll create sliders for a and b that I can move to whatever I want. I could also just flat out type it in, but hopefully you know at this point that I'm more about trying to come up with a method that I could use repeatedly than to come up with something that's a one-off. All right. So assuming I typed it in correctly, the expression, I don't need the whole function. I would just toggle the a to a 1, which I already have. The b, I'd toggle that over to a 3. That says a -1. And now what I do personally is I start messing around with the a value and the b value to see if I ever get a value that's bigger than a -1. It's a little bit of a self-checking kind of thing, right? So I just animate these bad boys and see where that gets me. Right? So this technique, a complete solution, but involving specifically the second derivatives test. Right? And it always feels like I'm saying that wrong, but I'm not. It is the second derivatives test. Because as you know by now, there's a bunch of different second derivatives that you could find. There's 4, not all of them unique, but there's 4 of them that you could find. All right. So yeah, you are really making use of second derivatives rather than a second derivative. All right. Second derivative test, that's Calc 1. That's for finding points of inflection, things like that. Actually, there's a second derivative test for Extrema in Calc 1. It's kind of interesting too. But that's neither here nor there. All right. So no matter how much this animates and slides, I'm not getting anything anywhere near. I mean, I'm getting a lot of like extreme values on the low side, but nothing bigger than a -1. So that's something to keep in mind. You could also, I mean, if you want to get cute with this, you can restrain your function with like a teensy tiny step. And have it go in even smaller intervals. I think it only goes nearest, the best it does is nearest 100th, and sometimes I can't even get that to work. So, like this is more for show than anything else, but it still gets the job done. All right, so let's stop that recording.